All right, we're going to get into the idea of function notation. So, let's talk about two different ways functions can be written, or equations can be written, I should say. So, we have explicit equations and implicit equations. So, explicit equations is an equation solved for a specific variable. So I'm going to write several examples. I could have y equals 2x plus 7. I could have x equals y squared plus 4. Or I could have, y equals x squared plus 2x minus 4. All right, so one variable is solved for. And the other side of the equation has a different variable. Right? An implicit equation is an equation that is not solved for a variable. So a very common one could be Pythagorean theorem. X squared plus y squared is 64. Right? We also could have y squared plus 8x equals 7. Or we could have something like xy plus 4 is 9. So not one variable is specifically solved for. Now, it doesn't mean we can't do that. In fact, we're going to do several examples right now where we're going to write each equation explicitly in terms of x. And then we'll figure out, is the equation a function? Okay. So when it says in terms of x, we want to solve for the other variable because we mainly want the equation to have x in it as the useful part, I guess. So this first equation, we're going to solve for y. And I'll even write that note here. Solve for, let me look at all these examples before I say solve for y. Yeah, all these examples have only x and y. So in this case, we are going to solve for y. All right, so we just want to isolate that variable. And so what I do is I say you work from the outside in. So anything on the opposite side of the equal sign is so far away, I don't have to deal with it. So to me, the outside is x. So to move x, I got to do the opposite of what's happening. That's a positive x, so the opposite of that is going to be negative. So I'm going to subtract x on both sides. So I have negative 4y equals 20 minus x. Or you can put the negative x first and have that negative x plus 20. And then the next thing in the way is that negative 4. It's attached to the y with multiplication. And to undo multiplication, we do division. So I'm going to divide both sides by negative 4. So y equals, let's see, 20 divided by negative 4 is negative 5. And negative x divided by negative 4 is a positive 1/4 x. And we can change that order and say 1/4 x minus 5. Might feel a little bit more natural for a linear equation there. And then, is this a function or not? So let's think about what that might look like. Or we can use a graphing utility and determine that. And this is a function. It's a linear function. All right, let's look at the second one. So x squared plus y squared is 25. Solve for y. So work from the outside in. So the outside is this x squared. This is attached with an addition, so we're going to undo it with subtraction. So I have y squared equals 25 minus x squared. And then to get y by itself, we have to undo the squared part. We can undo that by doing a radical with the index that matches the power. So square root in this case. So I don't have to write the 2 since it's understood to be 2 as a square root. But when you are the one performing the square root, like I just did, we have to account for both the positive and the negative square root. And that fact right there, because we have the positive and the negative, is the reason why this is not a function. We can plug it in a graphing utility and we will see that it looks, I don't want to put an accurate thing there because I don't know off the top of my head, but it's going to look something like this. A parabola that is sideways. That's going to fail the vertical line test. So, not a function. All right. Let's do another one. So we want to solve for y, so we want to do the outside first. So the opposite of subtracting x is going to be adding x. And then we want to undo the squaring, so we will square root again. And then we want to subtract 1 on both sides. So final answer of y equals, and I'm going to put that -1 out front and make that a -1 plus or minus the square root of 3 plus x. Just so it doesn't look silly on this outside and that I don't confuse it with being inside the radical. And this, again, because that plus and minus, the radical is not a function. All right, let's try this one here. So we want to solve for y, so I need to move everything else. So 1/2 x will subtract on both sides. And then this negative is on the most outside to me. So we're going to divide everything by -1. So we have cubed root of y equals -7 plus 1/2 x. And then to undo a radical, we're going to raise it to the power that is the index. So I'm going to cube the cube root. So cube both sides. I'm out of room, so I'm going to move over here. So y equals -7 plus 1/2 x cubed. And then you might also see it, and it'll look prettier if it's 1/2 x minus 7 cubed. Just looks a little bit more natural to not start with negatives there. But it's the same thing. And then this is a cubic equation here, and cubic functions are functions. Right? All right, let's keep going. All right, so I'm going to need to move the x. And then I need to divide by -1. And then I need to undo the radical by raising it to the power that's in the index. So 1 doesn't have 1, so it's understood to be 2. And then I will subtract 1 from both sides. So I'm left with y equals x minus 8 squared minus 1. This is a quadratic, and yes, it is a function. All right, I guess I should pause here. I am looking at these with the knowledge that I have about functions and function families, which does come later in this this class. So if you're not following how I'm looking at that and knowing yes, function or no, not a function, we can graph it. We can plug it in our calculator, we can plug it in Desmos, and we can look at it visually. Okay. And then I'm going to solve for y. So I'm going to do something a little crazy here, because I want to move things that are on the outside. So I want to move that 1 first. So I'm left with xy minus 5y equals 2x plus 1. And now both of these terms here, right, they have a y. So I can think of this as one of two ways. I can think of this as, let's pretend we had 2x minus 3x. We would say that's -x, right? Because we combine the coefficients because they have the same variable. right? So I can think of that the same way and say, hey, they both have a variable of y, and I just subtract the coefficients because I have x minus 5, right? Or I can think of it this way and say they both have a y, so let's take a GCF out of y, and I'm left with x minus 5. So either way, that's what we're left with. Because then I can divide by the entire quantity of x minus 5 on both sides. And y equals 2x plus 1 over x minus 5. And this is a rational function. So yes, it is a function. All right, so let's move into function notation. Because while we have solved all of these for y, there are many different notations as we move through this course and the following math courses, right? So you might want to look at many equations at one time, and you don't want to keep saying, oh, y is 2x minus 5 and y is 3x minus 4. You know, maybe those things are not both the same, right? So to do that, we can give equations different names. So that's where this function notation comes in. So we might say our equation is y equals 3x squared minus 5. But in function notation, we can substitute the y for a name. F of x. Doesn't have to be f of x. I do think mathematicians, I always say this at some point, that mathematicians are lazy. So we start with f of x because f is a function, right? And then usually what follows is the rest of the alphabet, right? You got g of x, h of x. Haven't really seen an I of x, but I think technically you could use it. But we can say f of x equals the 3x squared minus 5. And then we would read this as f of x. So it's a function f at x. And again, doesn't have to be f, but that's usually what we start with. All right, and then once we're in this function notation, we can better evaluate the functions. Because, yeah, we could say y equals 3x squared minus 5, and we could say, hey, what's y if x is 2? Perfectly valid. But this is what is seen a lot more common as you move through math, is this right here, f of negative 5. You're given a function, so f of x equals x squared minus 6x plus 23. And we want to evaluate f of negative 5. That's saying that x is negative 5, right? So I could say, all right, so f of negative 5 is, and then wherever there's an x, I will put the negative 5. So negative 5 squared, and I always throw parentheses around it just so I don't mess up any negatives. So negative 5 squared minus 6 times negative 5 plus 23. And then at this point, it does become a calculator problem if things are allowed to have a calculator. I always say that my 7th grade math teacher took away our calculators. So I always am used to doing it with no calculator. So negative 5 squared is 25, and then plus 30 plus 23. So f of negative 5, let's see, that's 55, 78. So 78. Let's try again for this function. So see what I mean? We don't always have to have f of x. So this is h of x. H of x is 7 minus x squared, and we want to evaluate h of 9. So h of 9 is 7 minus 9 squared. So h of 9 is 7 minus 81. So h of 9 is going to be a negative 74. Okay. Try it with some more functions here. Got a rational one here. So p of x is x plus 1 all over 2x squared plus 4x minus 13. And we want to evaluate p of 4. So substitute 4 in wherever there's an x. Right, so 4 plus 1 over 2 times 4 squared plus 4 times 4 minus 13. And I'm just going to follow it to the right here. So 4 plus 1 is 5. 4 squared is 16. 16 times 2 is 32. 4 times 4 is 16. 32 plus 16 is 48. And 48 minus 13. Let me do that off to the side. 48 minus 13, 35. And then we have a fraction, 5 over 35. We can reduce that because both of these can be divisible by 5. So we get 1/7. Right? G of x is x cubed plus 3x squared plus 7x minus 4. We want to evaluate g of negative 2. So g of negative 2 is negative 2 cubed plus 3 times negative 2 squared plus 7 times negative 2 minus 4. All right, so negative 2 cubed is negative 8. Negative 2 squared is 4. 4 times 3 is 12. 7 times negative 2 is negative 14. And then minus 4. And let's see if I can do all this in one step. So negative 8 plus 12 is 4. 4 minus 14 is negative 10. Negative 10 minus 4 is negative 14. All right, q of x is the square root of 6 minus 2x. And we want to evaluate q of negative 15. So q of negative 15 is 6 minus 2 times negative 15. So 6 plus 30, which is going to be the square root of 36, which is going to be 6. Now, I'm sure some of you might be thinking, well, what about negative 6? That also gives 36. And that's so true. It does. But the radical that was given to us was the positive square root. Okay? So we're just going to take the positive 6. If you're the one performing the operation, like at some point you were solving and you had to square root both sides to undo something, then you have positive and negative. This was already given to us. So, positive 6. All right, an absolute value functions. P of x is absolute value of 1/2 x minus 14. And we want to evaluate P of negative 10. So P of negative 10 is the absolute value of 1/2 times negative 10 minus 14. So 1/2 of negative 10 is negative 5. Negative 5 minus 14 is negative 19. And then the absolute value of negative 19 is positive 19. All right. Ooh, an exponential here. F of x is 5 times negative 3 to the x. And we want to evaluate f of 4. So f of 4 is 5 times negative 3 to the 4th power. Let's see, negative 3 to the 4th power. I just write it out 4 times. 9 and 27, 81. And the negatives match up. So it's going to be a positive 81. And then 5 times 81 is going to be 405. Or 405, I should say. All right, a of x is the negative cubed root of 2x minus 7 plus 1. So I gave that pause there because that plus 1 is on the outside of that cubed root. And we want to evaluate a of 17. So a of 17 is the negative cubed root of 2 times 17 minus 7, and then plus 1. So negative cubed root, 2 times 17 is 34. And then 34 minus 7 is 27. The cube root of 27 is 3. So the negative cube root is negative 3. And negative 3 plus 1 is negative 2. All right, so all of the examples we have done so far have been evaluating functions with just numbers in them. We can evaluate functions with letters. So like this one says f of x equals x cubed plus x squared, and we want to evaluate f of 3y squared. And that's possible. Because all we're doing is substituting in a value into the input in the function. So wherever there's a x, I'm going to substitute in 3y squared. So I have 3y squared cubed plus 3y squared squared. And we could use exponent rules to simplify this out. So 3y squared cubed, I can distribute that exponent to the 3 and the y squared. So 3 cubed is 27. And then y squared cubed, exponent rules say it's a power to a power. So we're going to multiply those exponents. So it's going to be y to the 6. And that same idea can be applied for this squared. So 3 squared is 9. And then y squared squared is y to the 4th. And then these are not like terms, so we cannot combine them. So I would stop there. You could argue we could take out a GCF and simplify it, but we're not going any further with it anyway. So 27y to the 6th plus 9y to the 4th is just fine. All right, we have g of x is 3x minus 10 all over x plus 5. And we want to evaluate g of negative 5c. So g of negative 5c is 3 times negative 5c minus 10 all over negative 5c plus 5. And then I'll see if I can simplify anything. So 3 times negative 5c is negative 15c. And I still have that minus 10 that was there. And then I have minus 5c plus 5. And then what I am seeing is a lot of 5s. I see a 15, a 10, a 5, and a 5. So I think I could divide all those terms by 5. But what I'm going to do is I'm going to take out a GCF to do that. So I'm going to take out a negative 5 just because both of these leading terms here have negatives. So I'm going to take out a negative 5. I think it'll look a little cleaner when I simplify this. So I'm left with 3c plus 2. And then the denominator, I'm going to also take out a negative 5 to be left with c minus 1. And then negative 5 over negative 5 is a positive 1. So I'm left with 3c plus 2 all over c minus 1. All right, and now those two examples were monomials, right? So that just meant one term was substituted in. These next examples, we're going to substitute an entire expression in. Okay, so h of x is x squared minus x minus 1. And I want to evaluate h of 2a plus 7. So anywhere there's an x, I'm going to substitute in 2a plus 7. So 2a plus 7 squared minus 2a plus 7 minus 1. And because I think some terms are going to simplify out, let's go ahead and keep going. So 2a plus 7 squared, I cannot do the same exponent rules as I was doing before, where I had just distributed that exponent to the coefficient and to the variable. And I cannot do that because that only works with monomials, right? So what I have to do is I'll do some side work here. I have to do 2a plus 7 times 2a plus 7. So you might have seen this before, and you might have seen it called FOIL, for first, outer, inner, last. I'm not a fan of that, only because that doesn't work for terms that are more than 2 by 2. So you could double distribute is really what that foiling does. So you're distributing the first term to both, and then you're double distributing, so you're distributing again. Or there's the box method. I think the box looks nice for organization, especially when you get to something more than just 2 by 2. So I'm going to show that one here. So we have 2a plus 7 times 2a plus 7. And then we're finding the areas of these little boxes. So 2a times 2a is 4a squared. 2a times 7 is 14a. Then I have another 2a times 7. So another 14a. And then 7 times 7 is 49. And then I want the area of the big square. So I'm just going to add all those pieces together. And not all the time, but sometimes the diagonal is the like terms. So what I have here is 4a squared plus 28a plus 49. And I'm so sorry, that does look like it says 4a. So that's just my first part. That's the 2a plus 7 squared. I also have to distribute this negative because I'm subtracting off this entire quantity. So minus 2a minus 7. And then I have that minus 1 that was back there at the end. It's not in that parentheses, so it does not get that negative 1 distributed to it. And now let's just combine some like terms. So the 28a and the negative 2a is going to give me what, 26a? And then I also want to combine 49 minus 7 minus 1. So 49 minus 7 minus 1 is 41. So my final answer here, h of 2a plus 7 is 4a squared plus 26a plus 41. All right, we have k of x is 4x cubed plus 7, and we want to evaluate k of m minus 1. So k of m minus 1 is 4 times m minus 1 cubed plus 7. All right, so let's cube this out. So here, you know what? I'm going to go back over to where I have a little bit more space. I'll get to show you the box with more than 1. So it's m minus 1 cubed. All right, so I'm going to do the box with the first one, right? So I got m minus 1 and m, oh my gosh, m minus 1, m minus 1. So that gives me m squared minus m, and then a positive 1. So that gives me m squared, combine like terms, so negative 2m plus 1. But then I have to multiply it by m minus 1 again. So if I go with this box method here, right, I can split into those 3 terms. And then I can do m minus 1 again and fill it out. So I'd get m cubed minus 2m squared, and then m, and then negative m squared, and then 2m, and negative 1. And again, it's not always going to happen, but look at these diagonals. They're the like terms. So I get m cubed minus 3m squared plus 3m minus 1. How cool is that? And then I've written it over here to the left. I'm just going to go ahead and distribute a 4 as I bring it back over. So it's going to be 4m cubed minus 12m squared plus 12m, and then minus 4. And then I still have that plus 7 in my equation, right? So a final answer of 4m cubed minus 12m squared plus 12m plus 3. All right, so we've done function notation given the equation, but we haven't done function notation, or function evaluation, I should say, from a graph. So we have a graph, cool, right? We want to evaluate f of 1. So it's still the same concept that this 1 is the x value. So I'm going to go over to the graph, and I'm going to look for an x value of 1, And I'm going to follow it down till I get on the graph. So this one happens to be the vertex here. But f of negative 1 is 1, 2, 3, 4, 5, 6, 7, 8, negative 9. Okay, I'll do another color. F of 5. Same idea. We're going to go to where x is 5. So 1, 2, 3, 4, 5. But then I want to follow it up to where it is on the graph. So right here. And then I just want the y value, which is 1, 2, 3, 4, 5, 6. Okay, I'll erase my drawings. F of negative 2. So negative 2, it's right there on the axis. So 0. And then f of 0. So x value of 0, follow it down to the graph. So it's 1, 2, 3, 4, 5, 6, 7, 8. So negative 8. All right, and there we have it for that section. So if you have any questions, let me know.